In this example, we're asked to use the momentum integral theorem to determine the friction coefficient, the dimensionless boundary layer thickness, momentum thickness, and the dimensionless boundary layer displacement thickness for a laminar flat plate flow with no pressure gradient, given this sinusoidal velocity profile, where delta is the 99% boundary layer thickness, and y is the distance from the plate surface, and use the outer flow speed. So we're asked to compare that result that we get from that sinusoidal profile to the Blasius exact solution. So we'll go through the Kármán momentum integral equation approach. So let's go ahead and write out the Kármán momentum integral equation. So we have the wall shear stress divided by the density is equal to the derivative of the momentum thickness times the outer flow velocity squared plus the displacement thickness times the outer flow velocity times the gradient of the outer flow velocity. And since we're told that this is a flat plate flow with no pressure gradient, then the outer flow velocity will be a constant. Since there's no pressure gradient. That comes from Bernoulli's equation. And so we can go ahead and rewrite that equation a little bit more simply. So since the outer flow velocity is a constant, the du dx term will be 0. And then this velocity can come outside the derivative. And so what we're left with is the following. Okay, so that's the equation we're working with. That's just the simplified Kármán momentum integral equation, given that the outer flow velocity is a constant. Okay, so what we need to find then is the momentum thickness in terms of the 99% boundary layer thickness. So let's go ahead and write out the momentum thickness integral. So this is just from the definition of the momentum thickness. And what we need to do now is substitute in our given velocity profile into this expression. Since this is given in dimensionless terms, so like little u over capital U and y over delta, let's go ahead and write the y term in terms of y over delta. So let's do that. So if we do that, it'll look like the following. All I've done here is I've divided the y by delta, so that means that my upper limit on the integral should just go to 1, and then I need to bring a delta outside since I have a delta here. So you see the deltas multiply out. Okay, so now we can go ahead and substitute in our given velocity expression. So this will be a sine of pi over 2 y over delta times 1 minus sine pi over 2 y over delta times d y over delta. If it is easier to understand, we can go ahead and just make that y over delta equal to an alpha everywhere, so you can see it a little more clearly. So that's the integral that we need to solve. So we can go ahead and solve the integral. Let me write it just one more way here, and then we'll go ahead and solve it. All right, so we can go ahead and solve that integral, and I won't go through all the steps of that, but you can use an integral table to look up the results for this integral. And if you work it all out, you'll get the following, that the momentum thickness is equal to delta times 2 over pi minus 1/2, which is about equal to 0.1367 delta. Okay, so now we can substitute this expression back into our Kármán momentum integral equation expression right up here. So let's go ahead and do that. Oh, actually, let me bring the numerical value out front. Okay, so now that's what we have. So this is just substituting this momentum thickness expression back in right up there. Okay. So now we need another expression in order to solve for our 99% momentum thickness. So we have another way to find the wall shear stress, and that is just using our standard expression tau w is equal to mu times du dy evaluated at y is equal to 0. This is just the shear stress at the wall using our given velocity profile. But since, again, we're dealing with the velocity profile given in dimensionless terms, let's rewrite this expression in dimensionless terms. So this will be like mu times capital U times d little u over capital U all over delta times dy over delta. And that'll all be evaluated when y over delta is equal to 0. So that's like mu times capital U over delta d little u over capital U over d y over delta evaluated when y over delta is equal to 0. So we can go ahead and substitute in for our velocity profile. So recall that our velocity profile, let me just rewrite it here so we don't have to keep moving the screen up and down. So that was our velocity profile. So when we take the derivative of that, we'll get pi over 2 cosine pi over 2 y over delta. And we're going to evaluate that when y over delta is equal to 0, so that'll just be equal to pi over 2 mu capital U over delta. Okay, so that's the wall shear stress just evaluated using our standard mu times du dy expression. So now we have two different expressions for the wall shear stress. This one coming from the Kármán momentum integral equation, this one coming from our standard approach for finding the wall shear stress. And we can set those two equal so that we have one expression with one unknown, that unknown being the 99% boundary layer thickness. So we'll set those two expressions equal. And then we can go ahead and solve this differential equation. So let's go ahead and do just a little bit of rearranging here. So we'll bring the deltas to one side. We'll bring the x terms to the other side. Oops, let me rewrite this. Make sure I have all of my terms correct there. Okay, and then we can go ahead and integrate both sides. When I integrate the right-hand side, I'm integrating with respect to x here. The viscosity, density, and outer flow velocity are not functions of x, so I can just go ahead and integrate that way. And what I'll do is I'll say the boundary layer thickness is 0 when x is equal to 0. All right, so we can go ahead and integrate the left-hand side. We'll get a 1/2 delta squared. The right-hand side, if I work out the numbers for this pi over 2 divided by 0.1367, that comes out to be about 11.4908. So we'll just write that. Okay, so there's our expression so far. So let's go ahead and rearrange to put it in terms of just the 99% thickness divided by x, just to make it dimensionless. So if I do all that, we'll get the following. Let me erase that so it's a little cleaner. So that's just some algebra there. And if you'll take a look at this expression, that's just 1 over the Reynolds number based on x. So our final expression then is our dimensionless 99% boundary layer thickness, about 4.8 times, or divided by the square root of the Reynolds number based on x. So that's what we get from our Kármán momentum integral equation approach. And if you recall from the Blasius solution, which is considered the exact solution for a laminar boundary layer with no pressure gradient, the delta over x was about equal to 5.0 over the square root of the Reynolds number. So we're awfully close with this sinusoidal velocity profile approximation. We're only about 4% different. So it's not too bad of an approximation. Okay, so now that we have that expression for the 99% thickness, we could go back up here and solve for our momentum thickness. If you recall, we had the momentum thickness is equal to about 0.14 times delta, so we could certainly substitute in for that. And if you do that, you'll get the momentum thickness over x is equal to about 0.6553 over the square root of the Reynolds number. And that's only about 1% different from the Blasius solution. The Blasius solution, let me just write this down, for the momentum thickness made dimensionless by x is 0.664 over the square root of the Reynolds number. So we're very close to that expression. Now if we want to find the displacement thickness, recall that the displacement thickness is the integral from 0 to delta of 1 minus little u over capital U times dy here. And again, if we want to put this in a dimensionless form, it'll look like this, just be delta times integral from 0 to 1 minus little u over capital U times dy over delta. And we could substitute in our velocity profile here, sine of pi over 2 times y over delta, and integrate that, and then substitute in for our expression for delta. So first of all, let me just go ahead and solve this integral. I won't go through all the detailed steps of that. I'll just show you the final result. It'll be equal to delta times 1 minus 2 over pi, which is about equal to 0.3634 delta. And then since we have our delta from up here, we could substitute that in right here and solve for the displacement thickness. So that comes out to be about 1.7420 all over the square root of the Reynolds number. And that one is only about 1% different from the Blasius solution. If you go back and look through your notes for the expression for the displacement thickness for the Blasius solution, it's about 1.72 over the square root of the Reynolds number. So we're pretty close to that. Now the very last thing that we're asked to find is the friction coefficient. And if you recall, the friction coefficient is just defined as the wall shear stress made dimensionless by the dynamic pressure based on the outer flow velocity. So our wall shear stress we had found earlier in the problem. We'll just use this expression right here. See, here's the wall shear stress, just pi over 2 times mu capital U over delta. So let's write that down. It was pi over 2 mu capital U over delta. We're making it dimensionless by the dynamic pressure based on the outer flow velocity. And so if we simplify this down, this will end up being pi times mu over rho u x times x over delta. And then we can go ahead and, well, first of all, you see that this is just 1 over the Reynolds number based on x. And then the x over delta, we have that expression that we solved for right up here. So we could substitute that in. And if we do that and simplify everything down, then our friction coefficient is 0.6553 all over the square root of the Reynolds number. And this is also about 1% different from our Blasius solution for the friction coefficient, which was 0.664 over the square root of the Reynolds number. All right, I think that's everything we were asked to find in the problem. So this is a good example dealing with the Kármán momentum integral equation. The general approach here was to use the momentum integral equation here. We know that the outer flow velocity is a constant because there's no pressure gradient. The key line here is there's no pressure gradient. Just remember that from Bernoulli's equation. Let me just write this out. Here's Bernoulli's equation. We don't worry about the elevation differences because they're very small. But if we take the derivative of that, we'll get the following. So if the pressure gradient is 0, then that necessarily means that U has to be a constant. Since U in general is not 0, it means du dx has to be 0, which means that the U has to be a constant. So knowing that there's no pressure gradient means that the outer flow velocity is a constant. So we simplified our momentum integral equation. We evaluated what the momentum thickness was in terms of the 99% thickness, just using the definition of the momentum thickness here. And then we substituted in our given velocity profile, which is an approximation, based on experimental data. You might say the boundary layer velocity profile looks sinusoidal, so you substitute that in. So we got an expression for the momentum thickness in terms of the 99% thickness, plugged it back into the momentum integral equation. We also found another expression for the wall shear stress, just using our standard mu times du dy, but evaluated at y is equal to 0 since it's the wall shear stress. So now we have two expressions involving the 99% boundary layer thickness. So we set them equal to one another here, solve that differential equation, indicating that the boundary layer thickness is 0 when x is 0, and then we ended up with our final expression.